Ladies and gentlemen, please welcome to the stage Linda Cadwell Stancin.
Okay, welcome back. I'm going to give a little level set on who I am because who's this person standing up here? I am the leader of research and development for General Motors. I am relatively new, so I have a lot of friends in the audience that help me out. So I want to thank Dr. Madhu Raghavan, who really puts a heart and soul into the center and also into the research that he does for GM. So I joined GM from Lockheed Martin, where I was Vice President of Research and Technology, and previous also the Vice President of Vehicle Engineering. So very different between the automotive and the aerospace and defense industries, but I see a lot of similarity. And it was brought to bear in Jason's talk, where he really talked about the intersection with the E between vehicles, AI, data, and we can see that also in aerospace. So I'm going to talk a little bit about our EVs. Now, GM R&D has an incredible history. It's an amazing history. But today I'm going to talk about the future we are creating for our customers, delivering products that people crave and experiences that they'll never forget. Okay, so our EVs are not just competitive, they're leading. We've got some of the fastest charging trucks available in the market. A Chevy Silverado can add an estimated 100 miles of range in 10 minutes using a 350 kilowatt fast charging. We also have the longest range trucks in the market, with a Silverado delivering over 490 miles on a single charge. That is incredible science. And I think about the work that Alan Taub did at GM and the history that he set, which impacts the entire industry. So a lot of that work came from Alan and the team in GM R&D. So we are all in on electric vehicles. We've got more than 10 electric vehicles across Chevrolet, GMC, and Cadillac brands. And as you heard yesterday, once someone owns a battery electric vehicle, they tend to stay electric. So loyalty consistently sits now around the 70 to 80% level in terms of rebuy. The experience with an electric vehicle builds confidence, and then confidence drives repeated adoption. In addition to that, now recently in the news, what you're seeing is a big pickup in used EV purchases. So there's more of an acceptance. That's an important market because it's often brand new buyers, first car buyers. So we're seeing that market pick up, and that's important. So in 2024, US Outlook projected about a 50% EV share by 2030. And updated forecasts show a much more moderate pace, projected to land around 27% in 2030. When we compare this to the global picture, though, China is accelerating towards an 80% EV share, and Europe is keeping up a steady upward trajectory. Other regions are also outpacing North America. And why is that right here in North America? We find that in our surveys and understanding the customer, range anxiety, higher upfront cost, and limited charging infrastructure remain the highest technical barriers in North America. So therefore, my message to you is, whether you're at GM or Toyota or you're an innovator here, is that we must tackle these technical problems urgently. So range, cost, and charging ease with new technology. And this is where the role of research and technology engineering around EVs is critical. I'm going to talk a little bit about our research programs. So at GM, we're now concentrating on very focused research programs which all have significant impact. So from product safety and integration, always very, very critical. It's the #1 result every single time when we survey buyers. It's that safety and reliability. And that is just as true with the EVs as traditional ICE vehicles. Connected and immersive experience. Why do I bring this up? There's a competition for the energy on the vehicle. Is that energy going to infotainment? Is it going to the AI assistant in your vehicle? Is it going to a super cruise or autonomous driving experience? Or is it going to propulsion? So that's a really critical area to focus on. Advanced battery research, we'll talk a little bit more. Of course, many of you are deep experts in that area. We're going to talk about the research program that Madhu leads, and it's called Extreme Vehicle Efficiency. Because what we really need to do is tackle the efficiency from a completely holistic focus, right? Rather than taking apart a battery cell or thinking about infotainment separately. We need to think about it all together. And then engineering and computational acceleration with artificial intelligence. It's roaring in, affecting every decision we make on the vehicle now. Robotics, AI and new semiconductor technologies and federated learning. Industry 6.0 is coming now, which means we need to move very fast, pick these capabilities up to be competitive and on cost. And then future factory, that smart, intelligent, adaptable, efficient factory. So all the technologies come together to affect the experience that an EV buyer has. They all matter. So let's talk a little bit about batteries. Okay, I've got cost on top. Right now, battery cost, battery system cost, the entire integration cost is too high. Oopsie, sorry, I gotta go back. Okay, it's too high. So when we think about new chemistries, when we think about the design of the cell or the pack or the entire propulsion system, we've got to tackle cost very, very quickly. The other thing we need to think about is energy density. We really have to expand range, especially for North American customers. They expect to say, hey, I'd like to go to Chicago. Hey, this consumer is a different consumer. It's not just a let's stay local consumer, I can charge it at night. Really important to address that. And then when we think about energy density, we need to focus on more range with less sacrificial volume. And then consumers don't really bring up lifespan in the surveys, but it matters to them. And it's really what they talk about with their friends. So lifespan matters. And drivers tend to like EVs for their power. We've talked about that, the power of the drive. I enjoy that. I got here a little bit faster because I could merge faster. And I really love my Lyriq, absolutely love it. So North American drivers expect high power in their vehicles for accelerating or towing heavy loads. Then charging security, we've talked quite a bit about that. It's a huge concern. We really have to make sure that the people feel like they have the charge that they need, and that when you're driving in Michigan in winter, that it's not a surprise that you have poor performance in cold weather. So finally, the buyers want to know that their battery is recycled or sustainable friendly, right? And again, reiterating safety #1. Now, I want to turn to everything besides the battery because it's all of it that needs to go. Make sure EVs are profitable and they increase market share. So we're going to talk about our research program called Extreme Vehicle Efficiency. There we go. It's a beautiful truck. So we're going to walk around this a little bit because it takes all of these areas. So it's driving step change vehicle efficiency across a full vehicle system, from aerodynamics, reducing drag, through advanced aero to lightweighting, system level mass reduction, propulsion, improving electric drive efficiency and controls across the full operating map, and optimizing energy conversion throughout the vehicle. And then AI-based tools. We're using a ton of AI. AI in understanding the drive experience, AI to do design for that electric drive, AI for manufacturing, AI for root cause analysis in production. So AI is a big, big deal. The rechargeable energy storage system, we're increasing cell to pack to vehicle efficiency, including voltage architectures and pack design, minimizing losses in power electronics, cabling, auxiliary loads associated with the battery system. Thermal, we're tackling holistic thermal management of the cabin, battery, and propulsion to cut parasitic loads. We're developing control strategies that maintain customer comfort while reducing HVAC energy use. We'll talk a little bit more about smart charging, and you'll hear more about that during the discussion time. AI, now aerodynamics, really want to focus on drag here, and we can do that through active and passive methods, rolling resistance, and the total design of energy utilization by the vehicle, whether that's passenger comfort or infotainment or the autonomous driving or propulsion. This was a film that they couldn't load because of the deep security of the University of Michigan. Which I thought was ironic. So we were quite ready to show you our advanced tools, but we'll have to do that another time. Okay, lightweighting, absolutely critical right now. Again, the total solution, both for our ICE-based vehicles and EVs, and doing this smarter. The only way that we compete with what's coming from overseas is really going after a brand new, holistic, total lightweighting solution. And then fast charging, we're going to talk a little bit more about this in the discussion time. Very, very critical. So I think you've heard a little bit about this, but it's something that we need to solve very quickly and get implemented across the country. And lastly, I want to just mention, this is areas of high fidelity multiphysics battery modeling. What we're seeing is we've been able to go from, basic molecular design now, right? Density functional theory, all the way to the chemistry of the cell, right? How it integrates into the pack and propulsion system. But now with AI, we're going so much faster. So we use a wrapper of AI around the calculations, which allows us to compute dramatically faster. And this is a story around the battery, but that exists for the entire vehicle. So we're seeing huge gains in the ability to optimize with AI, coupled with mathematical physics and chemistry models. So we'll get to talk a little bit more about that with our other speakers. So we're committed to an electric future. Very happy to be here with this incredible group. What you are doing is so important to our economy, right, and to our future. So thank you very much.
Please welcome Peter Green.
Well, good morning. I'm delighted to be back on campus after a decade, and thank you, Alan, for inviting me to participate in the symposium. So as I mentioned, I'm from the National Renewable Energy Laboratories, known as the National Laboratories of the Rockies, as a change. And the battery program is quite extensive. It goes from sort of supply chain questions to just extreme fast charging kinds of work to morphology and degradation, from scalable manufacturing, and certainly a lot of modeling. And a lot of our work is done with partners, a lot of industrial partners, a lot of academic partners. And yes, as a lab, we're also connected to Argonne and Oak Ridge and Lawrence Berkeley labs working in this area. So it's fairly extensive, just as a brief introduction to the work that the lab has been doing. Now, you can gather from what I've said, and certainly from your own experience, there's a whole range of chemistries there for these very diverse applications. And so an exciting thing, if you look, for example, work that Michigan is doing with Argonne National Labs, using AI to identify potential new chemistries. And certainly Argonne and other collaborators are actually doing the same thing. So there's a huge effort out there. Some work, for example, at Argonne, where you're combining AI together with robotics to be able to quickly test certain battery compositions. That's going to help to accelerate things. But a lot of this getting with these new chemistries is really trying to understand the properties, how things evolve. I just want to remind you again, as the battery operates, you're getting change in the morphology of the anodes and the cathodes and the electrolytes. That's a challenge. And it's been really, really hard to really understand over the years how this is going to work. But essentially, we're going to have to address this safety challenge, again, for investors and for the public. So here's an example of a graphite anode, and certainly one used for lithium-ion batteries. That bottom section that you're looking at right now, the dark section, was actually is an X-ray image, so it's X-ray tomographic image that's managed to image things at a nanoscale, relatively new technology. The middle strip, what you're seeing, is an AI rendition of showing you where the graphite particles are located spatially in 3D. The top layer is giving you an idea of not just the graphite particles, but cracks as well as pores throughout the entire system. So this is AI enabled, and so you can imagine then at some level, you can get a lot more information in 3D than you ever did before as in this case. Now, just to consider an example, NREL had a collaboration with Clarios. And the idea then is that they've designed an electrode and designed in such a way that there's a specific morphological features they're looking at it. What they like to do is take this from maybe just a single cell pack and manufacture it at scale. And so the idea then is that as you go through the manufacturing process, you start off with a prototype system, you know what morphologies you're after, and as you begin to produce this thing, in this case, a roll-to-roll application, the AI can actually real-time tell you whether or not what you've got is the morphology you need and essentially ejected to get into the right morphology. And so this has managed to speed things up quite a bit, again, taking advantage of AI. Now, just going back to the picture, the battery is operating. So you have an anode here, and the anode certainly is in contact with the electrolyte at one end, and of course there is the electrode. That interphasal region, those regions are also active. As you get the ions traveling across from the anode to cathode throughout operation, you're dealing with a number of processes, right? You're getting a lot of reaction kinetics. Depending on the electrode, if it's an oxide, you can have oxygen certainly in the environment. You can also get certain reactions that are happening. And so the chemistries change, the reactions can change. And based on the temperature, you can get thermal runaway kinds of challenges. So this becomes an issue and questions that remain unknown in these new chemistries. In lithium-ion batteries, a lot of these are well understood. I mentioned 2,000 papers are published just in 2022 as an example. So lots done there. It's a new chemistry where we need a lot more information for investors and consumers. So what you have to ultimately then with these new chemistries, you'd like to understand the abuse tolerance, one, and you also want to understand the hazards potentially from ejection of gases and particles. And so you like to ultimately put together a series of safe operating parameters, safe operating zones for these things. And so ultimately, you're going to rely on AI to do this. So here's an example of again, this is a schematic from a Nature paper by one of my colleagues at Michigan and collaborators. The idea is that you want to scale from a single cell to a pack. you want to understand the materials properties, but understanding the materials properties alone is not sufficient, because what you have then is you sort of have a dynamic phenomena occurring where you have these materials, very different chemistries in contact with each other. You're having a range of reactions that are occurring, and you've got to be able to understand that. And so you're going from that level, and you can actually perform experiments all the way at different scales, but you have very limited information. So that's the bottom line. The second line is you can put together these multi-physics models to try and give you some guidance, but they only have limited value. Taking advantage of AI, on the other hand, is a way to provide a bit more confidence in what you have. So we're not there yet, but this is a schematic showing in principle where we'd like to get. The good news in recent years is that we're now be able to do operandi kinds of measurements. So you can actually, for example, use neutrons as a way to image, and not widely known, to image the dynamics of lithium ions across an entire battery. You can begin to see that as one possibility. You can use electron microscopy to begin to get these 3D images, and then with AI, try and construct things carefully. So the analytical techniques have improved significantly. And now with combination of AI can provide a lot more confidence much more rapidly than we have in the past in terms of the development. So the good news is that in the near future, much of this will happen and the costs should be able to come down. So my concluding remarks are the following. There's literally limitless of combinations of battery chemistries. And what you find is that whether you have a liquid or solid electrolyte, even with the same elemental compound, the thermal runaway can be very severe. And so that's why you really need your real data. It's hard to extrapolate. Using a combination of AI and robotics in the future, you should be able to evaluate a number of systems very rapidly. And I think certainly once you do that, you can have a better understanding fairly quickly about what the abuse tolerance is and certainly parameters of the battery is going to operate rather effectively. There are too many chemistries, and so we're going to have to prioritize. You're going to have to prioritize in terms of where the research should be concentrated. You're going to have to prioritize in terms of providing a lot of data from the labs to the OEMs in terms of things. And you're going to also provide a lot of data to first responders when you have a real hazard occurring there as well. So it's an exciting time ahead, but it's a hard problem, but we've made a lot of good progress, and so we should be excited about the future. Thank you.
Please welcome Jason Siegel.
All right, thank you. So I wanted to highlight a couple of areas that the EVC funded research projects have started to address some of these questions and kind of show some threads throughout the projects. And so I titled this "In It for the Long Haul," but understanding degradation and safety, not just as the battery is manufactured, but as it survives through its first use in the vehicle, and maybe if it's lucky enough to get a second use for grid storage or supporting something beyond maybe how it was designed. And so one of the first questions as we start to think about this is, how does aging in the battery pack or in the battery cells affect safety? And so I kind of show this image from Berkeley that's pretty famous at this point, but it's looking at all these interior degradation mechanisms, right? And so if you kind of look at the battery from current voltage or just a measurement of capacity of the cell, right, it's really hard to take that one data point and go backwards and say what's going on inside the battery. And then it's even harder to go back and say, well, from that one data point, is that cell any more or less safe than it was when it was manufactured? And so I wanted to kind of highlight some work that was done at India National Laboratory to try and answer these questions. And in the end, the answer was, well, it depends. Well, okay, it depends on what, right? It depends on how aged the cell is or what the testing conditions were. And so we want to try to understand a little bit more about that. And so we think about what is the evolution of a cell failure, right? You typically have some abusive condition that causes damage to the cell. You get swelling due to gas generation. Eventually, the pouch is going to rupture. release some of that gas. Maybe some of that gas is hot enough that it leads the cell to thermal runaway. Maybe it doesn't, right? That depends on maybe the internal state of charge of the cell. And so we've started to think about, through some of these EV projects, particularly the Thermal 2 project led by Professor Bowman, trying to think about what tools do you need to characterize the gases that are coming out of the cell. And to sort of piggyback on Peter's comment, right, not just a tool that you could use for current lithium-ion cells, but as you get a new cell design, right, how do you understand the failure mechanisms and what tools you need to detect failure at the pack level. And then if you haven't seen Van Loo's poster from the work on sort of particles that are coming out of the battery pack, I encourage you to go look at that, right? Understanding these failure mechanisms and how that changes with different chemistry. One of the other things I want to point out is, okay, the changes in materials, not just in the battery pack, but the thermal insulation materials or the materials that are used around the pack also impact safety. So how do you start to think about, you know, as I'm mechanically cycling this battery pack or thermally cycling the battery pack, those material properties change, right? So how do they impact safety? And that's also something that we're tackling as part of the Thermal 2 project. And it's not just from a modeling standpoint, but how do you get people to collaborate across you know, simulation, modeling, and experimental characterization, and start to think about techniques like this frequency generation vibrational spectroscopy or SFG to understand what are the changes at the material level, right? So at the interface that determines the heat transfer rates that really help us understand, is this material gonna do the protection that we need, right, after it's started to be abused or after it's had maybe a minor failure, right? Is it still gonna work as it was designed? And so I wanna also highlight one of the other projects that I've been leading, which is the Battery 5 project. This is trying to think about how we use electrochemical impedance spectroscopy to try and understand more about the internal chemistry and what's changing inside the cell, but not just, you know, the sort of lab scale measurements that you could make, but how do you do this on board a vehicle? How do you do this at a fleet scale? Where do you put the models and data processing? If we think about building digital twins for these systems, right, there's privacy issues because one of the huge concerns is, okay, how I use this battery pack affects how the cells age, but that's also tied to the personal information of where I'm charging, when I'm charging, right? So some of that data maybe you want to put on board the vehicle and run a local model, but you want to take advantage of the fact that, hey, my neighbor's got the same EV, or, you know, somebody operating in Arizona in a hot climate, right, is operating the same EV, and maybe it's degrading a little bit faster, right? So I've got some preview of what I'm going to see in a year by this vehicle that's operating in a different climate. And so starting to think about how you share that data, how you treat that data and make it available to train models becomes very important. And so I want to highlight some of the non-destructive tools when we think about this, right? I want to collect data on board the vehicle. I can't, you know, tear that battery apart and use the fancy X-ray CT to try and understand what's going on, right? I've got to rely on measurements that are non-destructive to train these models if I'm going to do it with field data. And so we can think about, you know, kind of moving from the cycling conditions, the types of measurements that we can take, correlating things like cell volume change, resistance, and capacity loss. And then we kind of think about like fingerprints or the voltage capacity relationship of each individual electrode material as an identifying tool to say, do we have loss of material on the cathode or loss of material on the anode? And how do we correlate that to changes in the electrochemical impedance spectroscopy? And so I won't spend too much time on this, but the idea is if you do a low rate charge and discharge, you can kind of sort of get a pseudo open circuit voltage curve for the cell, and then line up that shift and scaling of each active material's utilization to try and correlate, right, loss of lithium inventory, the amount of lithium that I can cycle back and forth versus the active material loss. And then we're trying to correlate that with the changes in the impedance spectroscopy. And one of the tools that we're using to do that is a distribution of relaxation time. So if you think about fitting the impedance data, right? You can take equivalent circuits. We're working on physics-based models. But the challenge is, right, it's very hard to sort of fit these Nyquist plots. You can think about, you bring an expert into that loop and they know, okay, I tweak this parameter and I get a good fit, right? Well, how do you get AI or a machine learning model to generate that kind of fit that, maybe a grad student does and tweaks in the lab? So trying to think about ways that you could relate that impedance spectra in a different transform domain where each sort of time constant is separable and easy to sort of pick out. And then, okay, if it's not separable or easy to pick out, can I use environmental temperature or some other factor to help me separate that if I know something about the physics and the chemistry? And so one example of this, this is kind of a plot on the left here of how the distribution of relaxation times is changing as the cell ages. And we can see that certain peaks, right, start to evolve at different states of health of the battery. And we can start to try and correlate those to different aging mechanisms. And so one that we've identified through this work is looking at the correlation between the cycle aging temperature and then this R1 or sort of high frequency peak that's typically correlated with electrochemical impedance spectroscopy. And you start to think, well, okay, that's related maybe to capacity loss. Well, it's not correlated with capacity loss, but it turns out it was really well correlated with loss of active material on the cathode side. You start to think, well, why is the cathode showing up in a change in EIS on the anode? And so diving into the literature, you can see, right, these are well-known, well-studied sort of characterizations of transition metal dissolution that then goes and screws up the SEI on the anode. And so we see these trends in impedance, and now the question is, how do you train learning algorithms to go back and identify these characterization and use that for health prognostics? And so I'll leave this up to say that in terms of remarks, we are really good at working on hard problems, but we need industry to tell us, right, how these problems relate to sort of the real world and make an impact. And so one of the ways we do that through the EVC is transitioning IP and getting our ideas into commercial products, right? We at the university, maybe we do startups, but we're terrible at getting products out into the market. You all are great at doing that. And that's an area where we definitely can benefit from working. And then we're training the next generation of engineers. And I want to say, this work doesn't happen without grad students. They come, they learn, they leave, and everybody benefits. So I'll leave it there. Thank you.
And now your moderator. Please welcome Harvey Bell as the presenters return to the stage.
Well, thank you very much for some really great presentations. So I have a series of questions laid out in a broad range going from affordability to grid integration, AI, and university system workforce. So the first one, Linda, is for you. Considering affordability, vehicle range, charging infrastructure as major impediments is laid out by your presentation, which technologies are you most excited about that enable the electric vehicle market?
So really it's optimization of all of them. And now that we have real strength in artificial intelligence, agentic AI levels, we can really focus on optimizing the entire system. So as you heard from Jason and Peter, we're applying AI to the cell chemistry all the way to pack, up and up and up to, hey, how are we distributing power? How are we, even when we think about the load of the decisions that are made on the vehicle against the infotainment and the communications on the vehicle, we're able to optimize, let's balance in real time the loading and movement and consumption of power on the vehicle. Similarly, when you relate that to cost, you think about everything that we can do or are doing in manufacturing. So we're applying artificial intelligence to optimization of the entire construction of the battery, then also the construction of integration of the battery in the surround structure, and including the entire vehicle structure. So we're putting a huge amount of effort into using AI, agentic AI, explainable AI, and the next level of those capabilities in order to advance electric vehicle cost.
Great. Well, so you just talked a lot about AI. Yeah. Peter talked a lot about AI. So it would seem that we ought to add Peter to the discussion here. And working off Jason, can AI predict the degradation of battery chemistries?
It certainly can. One of the things to think about too, as you think about the operation of a battery, you have these ions being transported through these highly heterogeneous environments. And these environments are changing as a function of time as the battery cycles. And so there don't exist any really conventional mathematical tools or even mechanisms to really understand what happens. What you can do is if you can get a lot of data and information to feed AI, it can provide some predictions about sort of mechanisms of transport. It can be useful in trying to understand potential reactions that may occur at interfaces. And if combined with some of the multi-physics models, begin to provide some realistic insight into what's happening across the entire battery system. There's a lot of work to be done, a lot more work to be done out there, but this is just the beginning.
Great. So one of the things that transpired with a lot of the research that was getting done here, and particularly research that was funded by the EVC under Professor Matthew, is it strikes me in reviewing posters yesterday that EVs really have a new customer, and that being the independent service operators, and in our case, the mid-continent service operator, which is the interconnections for all the local utilities, from DTE to consumers. And in our case, it stretches from parts of Wyoming all the way down to Mississippi. And if EVs get aggregated into what people call virtual power plants, it's sort of a bad name, and start interacting with the independent service operators in the nation. So I was going to ask Jason, what does this portend for now? You've got a completely new, different uses cycle for batteries, as you know, grid operators are going to try and bid off to the, or the aggregators are going to try and bid off to the spot markets. So what does that portend for all the battery usage that now people like Linda's operation are going to have to comprehend?
Well, I think one of the big things that, you know, historically we think about, you know, even something as simple as a vehicle warranty being a mileage-based warranty. Mm-hmm. Well, what does that mean? What is an equivalent mile of, you know, cycling your battery pack to service the grid? There's certainly opportunities if you can optimize the state of charge that you're sort of parking the battery at when you're done using it. Maybe you could extend life by using it in a grid application compared to, you know, somebody who comes home every day, plugs in and fully charges their EV because they're trying to beat some notion of range anxiety, right? So I think there's a lot of opportunities to extend the usable capacity of the battery by doing better care of it. Maybe you're plugged in and you've got thermal management active all the time, and you can beat, you know, calendar loss that way. So I think it depends on the cell chemistry. The chemistry could be optimized to do that, and it makes a more compelling product if that becomes an upfront design requirement.
So, Linda, do you have anything you wanted to add to that?
Oh, yeah, you saw me jumping.
Yeah.
So, yeah, we've got GM Energy business, and what we're seeing is a lot of opportunity space and shared power. Mm-hmm. And that also, you know, addresses things more and more. We're seeing power loss or various weather events, and that allows consumers to have that security of, hey, I'm going to be able to, my vehicle is going to power my house to grid powers, so it's all completely connected. So I think there's a lot more opportunity in that space. And back to AI and optimization of physics. Well, the team has really, really worked hard to optimize charging and consumption, and really gone deep on the physics on what's happening in the charger and what's happening on the vehicle. And that has improved our efficiency in charging like 11%. So going deep on the physics and the combination with AI is helping the overall experience.
Would it seem also it helps solve the affordability problem, because if you can have your vehicle powered by renewable energy and then interface with the grid and sell back, then you can add, that's a revenue stream to your customer and should impact the affordability. So if this could be really dialed in and optimized, there's potential here, I think. Okay, so we've been talking about the research in the university. Peter, you've been involved in a lot of research along your career. How do you look at the university industrial national partnership and the value that universities can bring? What's unique?
Well, the partnership brings together, so the universe is very much in generation of new knowledge, addressing fundamental questions by and large. The labs tend to be more, some of the labs tend to be, like where I came from, tend to be very technology focused. And so collaborative interactions tend to be quite useful from that perspective in terms of doing things. The labs have facilities like neutrons and X-rays, where academics can actually do very deeper analysis of materials and systems that they can't do otherwise. And so it's a nice symbiotic relationship to advance science and to advance technology. The labs also have lots of industrial interactions, as do the academics. And so this public-private partnership, I think, is very effective and certainly more and more valuable in the future.
Linda, do you have anything to add to that?
Yeah, it's absolutely critical, and it was a little bit scary, I think, in the last year or so, and because we in industry rely on that partnership, absolutely rely on it. We need to stay very focused and deliver products, and so we don't spend as much dedicated separate time on basic science. We need the universities and the national labs to be powerful and healthy and connected. And, you know, I think about how do we together tell our story better to citizens to understand the value that citizens are realizing from this partnership. It is enormous value. We're seeing, we have collaborations with many with the University of Michigan, many with the national labs, and those collaborations not only are moving science to applied, but in many cases where we have an applied, project and we really need deep technical skill to move faster, that's where we're getting it. So we received like 4 R&D 100 awards, and many, I think all of them were collaborations with national labs and universities. So really important.
Right. So we all agree it sounds like this is really, really important. How do you do it more faster? What are the barriers to doing more faster? Peter?
It wasn't expected. So, from my perspective in the lab system, I felt that things were actually going quite well in terms of pace. The difficulty may be in trying to set some of the agreements and to address some of the legal complications of it. That's where patents, who owns what. I think that's where the roadblocks come. But the research generally proceeds, at least from my experience, a lab with 1,000 partners, rather rapidly.
Yeah. So Jason, and I'm going to come back to Linda on this one.
I mean, I think one of the challenges is thinking about, what is the sort of academic incentive versus sometimes the industry incentive are not fully aligned. And so figuring out, what are the projects that can be fully aligned and what are the projects that, can go so far along a development path and then they have to jump and transition to an internal project, or understanding and clearly defining kind of how that transition structure gets put in place, I think helps accelerate that pathway.
Well, and that's sort of where I was going toward the final thing. So we get this research. How do we get it in production faster so that when I get my next lyric, it's there?
Yeah, the lyrics are delightful.
Yeah.
So
We agree on that, but I want this is about my argument for the next one.
So
When does this all happen?
No, let's tackle that. So what we are doing is really consciously focusing on very specific goals. They're aspirational visions. So we set kind of a North Star vision for what we want to achieve. Then we drill down to say, here's the research that we need to do. We think about, okay, what are the targets on that research? Who do we collaborate with to achieve the results relatively quickly? So we're bringing labs, suppliers, and university in on the total research program. Whereas maybe that didn't happen in the past. Maybe it was like, okay, we'll provide funding and then a proposal will come in, and then we'll go figure out, we'll rank which projects, and then we provide that funding. We're doing our research very, very differently, where we're crafting the program, the roadmap, and then we're making an ecosystem to deliver the capabilities as quickly as possible. And we're also trying to make sure that in that ecosystem, we go do an experiment and the results turn out poorly. That's fine. That scientist still did fantastic work to provide a decision early.
Reminds me of
Yeah, I
Thomas.
want to add something.
Yeah.
So NREL has had a collaborative agreement with First Solar on cadmium telluride. And the research and the manufacturing are highly coupled to the extent that some of the advances that NREL may publish in a Nature Science paper eventually gets implemented in the manufacturing very quickly. And that's a very strong, highly collaborative example of really the benefits of the science coming from it.
Cool. So in terms of NREL, it sort of brings me back to some of your AI chemistry and the creation. It struck me in your slides that we're getting all these chemistries, but what about the nation's capacity to physically begin to test them and then get them to pilot plants? Do you see going from the virtual models generated by AI, promising chemistries to production? What are the barriers there?
I think first off, your points are very important. One is that there's a huge number of chemistries out there. You're just gonna have to prioritize them. They're gonna have to prioritize in terms of where the focus is gonna be. I think that's the first thing. The use of AI helps to accelerate a lot of the advances towards understanding and addressing potential safety issues. So it's a real plus from that perspective. The nice thing about AI is that the range of phenomena that occur in the batteries it operates are so complex that a lot of the conventional theories and mathematics that we have we don't understand it physically enough. But providing a lot of training data, and that's a big challenge. Will the company share a lot of the data that they have? Then you can build better and better AI models to do this. But AI really does accelerate things from that perspective, and prioritization is a big thing.
But you alluded to the complication of getting it integrated in the vehicle model. And in earlier discussions with Jason, finding people that would share training data is key. But eventually, we got to make things, to Jason's point.
Right.
And so how do you, where are the barriers to going from the AI chemistries to making them and testing them physically to understand all those complications?
Well, so first off, right, I mean, the AI can identify chemistries. Secondly, use of AI can help you identify and design electrodes in terms of the morphology. That can happen very quickly. And a combination of, the work at Argonne, a combination of robotics and AI can help you test certain things very quickly. So that's going to be very, very helpful. But the biggest challenge is the training data.
Okay.
Getting the data, getting companies to share things openly. There's a database on looking at risks and sort of failures. There's a lot of information there, but the other stuff, will people share this? That's where the challenge will come ultimately.
Okay, cool. So another question that is sort of divergent from this line here is certainly a holistic thermal electric design integration, right chemistry and all the vehicle needs. How do you go about shaping the autonomous vehicle of the future with all those complications?
So, of course, you need to know the total load and what is going to be demanded from running the autonomy, all the other features that you need, the climate, all the propulsion. And so doing that full optimization of all the energy needs is critical, and knowing advanced decision making. So that's something that really you're making decisions in that vehicle in real time. And right now what's happening is there's so many communications and decisions that have to happen on the vehicle. Then it's really about what Jason was talking about with Eaton is a lot of the signal prioritization, latency in signals and decisions on the vehicle. So having that science, both the electrical understanding, signals, comms, understanding 5G, for example, connectivity, all of that has to be understood. And then we apply, in many cases, we're using artificial intelligence to accelerate, do a wrap around all the models that we're using to really get to the best architecture to balance the needs of autonomy and the needs of power and the needs of connectivity.
Well, we're about going to get to Hook here shortly. So, Jason, with all this discussion, do you have anything you want to add?
I mean, I think that I'm really excited to see kind of where the EV Center research projects have been going, and I think the collaboration. One of the things that we've managed to do that I think helps accelerate that is to bring people together. You mentioned starting to think about this holistic vision of, here's the research, here's what I want to go, here's the teams that I need to bring around me to achieve that. And I think that's one of the things that I'm really proud of what the EVC has been able to do to make headway on solving some of these really hard problems.
Peters?
I would say this is in a particularly exciting time where we can accelerate things. We've been talking a lot about AI, but now we have new characterization techniques where you can actually, operando techniques where you can actually image what's going on real time in a battery. You can use neutrons to image the dynamics and spatial positioning of lithium as well as sodium ions. A few papers out there showing that. You can use magnetic spectroscopy to image some of the chemical processes going, X-ray fluorescence and other techniques. You can actually look and really evaluate these reactions that are occurring. X-ray scattering to look at changes in lattice parameters. So there's a lot more information now that we can get from these batteries than we could have even 3-4 years ago. So things are going to move quickly.
Linda?
Yeah, it's an amazing time for science and research right now. They're going to look back on this time and go, oh, that was a huge breakthrough time. And so, we get discouraged with ups and downs in market, but we really need to embrace the fact that right now, this is massive, big change in scientific capabilities and technologies. And we need to really focus those on good things. So, thank you.
Thank you very much.